Good morning. How's everyone doing today? Morning. Okay, 1 second, please. Okay, just 1 second. Let me bring up the screen share. All right, so on Monday, we talked about Newton's first law, and let's remind ourselves what that is. Newton's first law says if a body remains in motion, an object was at rest will stay at rest, and if it was in motion will stay in motion, unless there is a unbalanced force on it. So today we will talk about Newton's second law that has to do with, okay, now we do have an unbalanced force, and what does that do? So if a net force is not required to keep a body moving at constant velocity, right, except that will continue to move, then what does a net force do? Then the net force is not the reason to keep something moving, but to change the status of the motion. So the force, if you want to change whatever the object was doing, change the velocity, right, then it requires a net force, a unbalanced force. So the sum of all the forces acting on the object cannot be zero if you want to change the velocity. And remember, the quantity that represent the change is acceleration, right? The change divided by time, the change of velocity divided by time, or we say it's the rate of change in velocity, is represented by acceleration. So a force is required if you want to have acceleration. So force generate net force will cause an acceleration of an object. That is what we will explore for Newton's second law. This is based on experiments, and the relationship was also found through experiment. But we do have some really good intuition on this that we can build upon. For example, we know that a net force causes an object to accelerate. Then does the amount of acceleration will depend on what object you're talking about, or does it depend on how much force you're exerting? I think the answer we all agree would be it depends on both of them, right? So let's say you have a fixed object and you wanted to accelerate, have a bigger acceleration, then you would apply a bigger force, right? So if we're talking about the same object. But if you're talking about different objects, let's say you were throwing a can of soda with this force and you give it a certain acceleration. But then instead of the soda, you were applying the force to a gallon of milk, which has a much bigger mass. Then you were thinking to achieve the same acceleration, you would need to apply a bigger force, right? So both how much force you have and how heavy or how much mass the object is will affect how much acceleration you can achieve. So based on experimental facts, there is the Newton's second law, basically is telling us the acceleration, is depend on both the force and the mass. Okay, 1 second, let me bring it back. Here's a slide. And it's proportional to the net force. The bigger the force is, the bigger your acceleration. But it's inversely proportional to the mass, right? The bigger the mass, with the same amount of force, you're going to have a smaller acceleration. So mass is sort of resisting the acceleration. Force is what causes an acceleration, or you can write it using F net equals ma to represent Newton's second law. F net, the net force, is equal to the mass of an object times the acceleration of the object. So first, we are going to do some direct applications of Newton's second law, and then there will be a lot of problems, a lot of classical ones that you see that can be solved by Newton's second law. We have to break it down into multiple forces, add together. But before we do that, the next few questions will be focused solely on the direct application of net equals ma. So look, for example, if you have multiple forces, then the F net is simply the addition, the vector addition of all the forces. Here you have 4 forces, 1, 2, 3, 4, 2 and 3 cancel each other, and 1 and 4 give you an overall net force is to the right, because the one that's to the left, to the right is F1 is a little bit bigger. So this will be your F net, and you can see your acceleration is in that same direction. Right, this is what we talked about, and this is how it would be reflected using a free body diagram. So here's a question you have already done. It tells you the net force that is acting on the box is in the positive x direction. So what can we conclude from simply that information? Okay, so A says its velocity is parallel to x. Its acceleration is parallel to x. Both velocity and acceleration is parallel to x or neither. So looking at this, you know that right away, if the net force in the positive x, we know right away the acceleration is in the positive x. So B is correct. As far as whether the velocity is in the x or not, this is sort of similar to a question we did in the last class. Is you're not really concerned about the sort of the entire picture. You're only looking at the snapshot of that instant that, okay, the net force in this direction, all I know is acceleration is in that direction. We have no information about the velocity. It could very well be in the same direction as the acceleration, or it could be it had a different direction of velocity, and then you apply a net force is opposing the direction of the velocity. And that is not of our concern here. We don't care about which way the velocity points, and we can't really know without more information. So we cannot say anything about its velocity. All we can say is at that moment, the acceleration must be in the same direction as your net force because of the Newton's second law, right? So the bridge question, this one, B is the correct answer. One more question from the pre-lectures. This one takes a little bit more of a step than the previous one. So let's look at this together. So if it tells you at the initial moment, you have, you don't really know what the velocity is, okay? But you know that there's a force applied on it. The net force is to the right. And you know, at the next second, the velocity is V1 is upward perpendicular to the force. So from this information, can we sort of backstep finding out the velocity that's representing V naught at t equals 0, the initial moment? So what do you think? How do we use these different vectors to find the initial velocity vector? Which one of these would be correct? Anybody would like to share some thoughts with us?
So right now, we know that at t equals 0, the acceleration vector is pointing towards the right from the mass.
Okay.
But for t equals 1, that's from the picture, it's the same. So since V1 is vertical, we know that V sub 0 had to be somewhere over to the upwards left, because otherwise it wouldn't have been vertically balanced out in a sense by F. So so that's why I'd say that it's D, I think. I don't know, it's been a while since I did it.
It's a very good one. That's a very good way to think about it. Excellent. So if you're thinking of V naught as in a velocity sort of diagonally to the left, you can think of it as a x component or a y component. So that's one way to think about this absolutely. So I decompose my V naught into, you have a velocity that is traveling to the left, you have a velocity that's traveling perpendicular upward, but this acceleration sort of get a balance out this velocity or reduce that to 0 and leaving this one after 1 second, right? Leaving this V1 as a final velocity. So absolutely, that is a great way to think about this. And then you can see the key here is you know that the direction of your net force gives you the direction of your acceleration. So you can relate that to the change of velocity, right? Because acceleration is the change of velocity over time. There's a second way to think about this is let's just do vector addition. We want to know what is V naught, but we know that the change of velocity, which is represented by acceleration times time, sort of overall the average acceleration times time, is your final velocity at V1, right? So to find V naught, you can figure out the arrow by looking at this arrow and this arrow. So you can see that, okay, you can do a sort of a vector, instead of addition, doing a vector subtraction to do what is V1 minus acceleration A vector. Or you can do what is V1 plus positive A. So if this is V1, this is A. So the flip A is in this direction, negative AT. So these two added together give you V naught that is diagonally to the left. So you get the same result. So this is another way to look about this instead of breaking down your initial velocity into two components. So whichever method you choose to use is totally fine. And what this question is trying to get at is a direct application of the Newton's second law you just saw. Okay, so let's do a couple more of these direct applications. So this one, for you to think about, here we have a net force applied to a smaller block and a bigger block. The smaller one has mass m, the bigger one is 5 times m, and cause them to move together. Okay, and now let's compare the net force on the smaller block and the net force on the bigger block. Okay, so the F is the one that's pushing both of them. Okay, but in terms of the net force on each of them is not necessarily the F. Okay, so if I said the net force M, I misspoke. So the net force F is on M and 5M together. But if you look at them individually, there's more than just the F, right? Because you have normal force, gravity, maybe you decide that's not important. You have a force between the blocks. One is pushing on the other one pushes back. But you may think this is quite complicated, and I give you a hint that you want to think about the direct application of Newton's second law, okay? All right, so I'll go ahead and let you vote. This one, I don't think we need to discuss, so I will open up the poll and then we can vote directly here. All right, let's go for another 10 seconds. So if you haven't voted already, please do so. All right, any last minute vote at this point? Okay, so let me go ahead and close it and we can take a look. We pretty much have our answers spread out across these three different options. Okay. So some of the thoughts could be, let's for B, let me try to propose a possible reasoning for that would be, well, I see a same force F pushing on the two together. So possibly these blocks will have the same net force. So that might be reasonable, right? What about C, that the force pushing on little m is bigger than the force to push on 5m? I mean, I can propose a reasoning that maybe, well, the force you exerted is directly touching the m, not the 5m. Perhaps more of that force is given to the little m rather than the 5m. What do you guys think about that? I mean, maybe that's not how you think about this at all, but that's just some possible reasoning that it's reasonable, right? You might rely on answering this question. And then you notice that these different reasonings all give me different results. So what should I do?
I kind of thought about something that like it was a really bum experiment, but I kind of just had a water bottle on my desk and I got my phone and I started pushing it. And I know my phone for a fact has less mass than my water bottle. At that point, I hadn't drank anything from it, and they both had the same acceleration. So I had already been thinking that they were equal, but the reason if you look at like the formula, the mass difference, if they have the same acceleration, the force on the 5-1 should be bigger, on the 5m should be bigger than m. But also it's the same force being applied by me because we said acceleration doesn't cause force causes acceleration. So then if they both have the same force being applied to them, maybe it's because we can just consider it like one overall mass for our purposes, maybe.
So one, you said you had, from what you have told me, I felt they were two different reasoning that are not agreeing with each other, right?
Yeah.
One, that they're equal. One require a bigger force to accelerate, which is your water bottle because that's a bigger mass.
Yeah.
That's excellent. That is exactly what we want to do with problems like this. We want to be able to sort through these inconsistencies. So what we just said is, yes, this is the same force being applied by us to two different objects, but the question is asking about the net force, realizing that if I were to draw my free body diagram on little m, I would have, okay, the force that is pushing little m, and I probably will get some kind of force of 5m pushing back, right? And if you're looking at your free body diagram on the 5m, here I'm ignoring anything in the vertical direction because that is not relevant. This F, when we say gravity is the only long-range force we're going to have, is this force is not directly touching your 5m. So we can, even if you apply them on the two of them together, you cannot put this F over here. You cannot put F on 5m. That would be wrong because it's not touching the 5m. However, you do have a little m touching the 5m, and that gives it a pushing force that's from the little m to the 5m. So how big is this compared to this, that's not our concern. And all we care is, okay, you have multiple forces acting on little m, and there must be a net force, net total. And you have this force acting on 5m, maybe they will even have some friction, right? We don't even know. It doesn't matter. All I cares is asking about this net force. And you can do this direct application of going back to your Newton's second law equation is, one thing I do know is they do share the same acceleration. Because they're moving together, it's impossible for them to not have the same acceleration. Then they're not going to be touching each other, right? So if they have the same acceleration, one is going to be 5ma, one is going to be ma, right? This is a force on little m, this is a force on the 5m. So this one is definitely smaller because it has a smaller mass. It requires an overall smaller force. Okay, so the answer would be A is correct. Going back to this force in between them, we will do more analysis later on. You can even go back to find out, okay, so how strong is this 5m pushing back on m? How strong is this little m pushing on 5m? You can apply individual, you can second law on individual objects and to find that out. But at this point, we're not, we don't care about that. So any questions? Have we sort out our inconsistencies in our reasoning?
So then essentially, since it's kind of, in other words, kind of confusing to determine the actual magnitude of the force being applied, we should always refer back to the equation of F net to find that, correct?
Yes, so depending on the question, this question is asking simply about F net. So you're not going to worry about the individual forces, but we do have a lot of problems asking you to solve the individual forces. So you can easily solve that because this F is applied to 1m and 5m together. So you can quickly do a Newton's application on them together because they are together. So the overall mass will be 6m, and you can solve for this acceleration being F over 6m. So you can use this acceleration and plug it in with Fm directly, knowing that, okay, this force is causing it to have this much acceleration. And I know the force is going to be F, 5F over 6 is how strong the little m is pushing it. So that you can really do as well, but we're just not getting there yet. Does that make sense?
Yeah, and I was a little confused as to why we didn't kind of look at the vertical forces.
We didn't do it because we know there is no acceleration in the vertical direction. We know that normal force and gravity will balance out. We will do more examples, and because for the simplicity, I did not want to draw it. I could draw these two forces, but we are not going to look at the motion in that direction because it's irrelevant, right?
Right. Okay. Thank you.
Of course. Thanks for the question. Okay. One more. So this is the one you have already done. So that should be really, really fast. We're doing with circular motion now with a constant speed, and you're driving around a horizontal circular track. So it's asking about the net force acting on your car. If you were trying to think about this using, think about the forces on the car, we might get really confused, right? But if you, again, relying on what we know about a Newton's second law is, what about the car's acceleration? We know that for an object moving in circular motion, even though the speed is constant, so the velocity magnitude is not changing. However, the velocity's direction is changing, and you need an acceleration to give you the change of the direction. And we call it centripetal acceleration, right? And what is the direction of that acceleration? So how do I draw the acceleration at this point?
Towards the center.
Toward the center, very good. So no matter where you go, you need this centripetal acceleration to constantly change your direction of your velocity. So we know that if your acceleration is toward the center, the net force must also be toward the center. So you can quickly apply that, and knowing that points radially inward toward the center of the circular track would be the correct answer. Right? So that's, again, a direct application of Newton's second law. Here we're only looking at the net force without breaking down into different forces components. Okay, so now we're going to do some more examples where we expand the left side of the equation, F net. F net consists of many forces, right? One of the forces we almost always have to consider is the gravitational force, so gravity. We haven't so far talked about how to calculate gravity, but here it is simply, you know that when an object is in free fall, gravity is the only force acting on it. So the net force is gravity. That's it. That's the overall force, is gravity itself. So F net equals ma, and we know in free fall, all objects on Earth fall with an acceleration of 9.8 meters per second squared. So that means my gravity is going to be mass times little g pointing downward. Okay, so if you had defined upward to be positive direction, for example, you want to write your gravity to be a negative mg because it's pointing downward. So Fg is always equal to m times gravitational acceleration, little g. Okay, but you can define your positive direction in whichever way you like. So this is gravity. We will use it a lot in our analysis. One thing that we want to be very careful, oftentimes we talk about the weight, and then we know that it's actually not the same as mass, even though it can be very confusing. If you use your daily experience, right? You go to the grocery store, you buy something, and they'll tell you how many pounds, right? And a lot of times that is a pound for mass. That is not the pound for weight. That's why it can be very confusing. Just knowing that when we talk about gravity, when we talk about our weight, we are referring to a force. Let's say the weight of the person is 120 pounds. Well, that is your weight. That means that is how much force the Earth is pulling on you. That is the force quantity, which is different from the mass quantity. You can see that force units for force, here is what we did with unit dimensional analysis. Remember at the beginning of the course, we said, if you want to get the dimension of something, you take the left-hand side and the right-hand side, their dimensions should be equal. So the dimensions of the force, or the unit of the forces, add a square bracket on it, is equal to the dimension of the mass times the dimension of the acceleration, right? The dimension of the mass is just mass quantity. The units is kilograms in the standard units. Acceleration is meters per second square in the standard units. So the dimensions for the units for the force is kilograms times meters over second square. And we call that 1 newtons. So that is the SI units for 1 Newton is kilograms meter over second square. So that is the units for the force. You can either write newtons or you can write it using the fundamental units. That's also fine. You can change back and forth between mass and weight very easily, because if someone has 50 kilograms of mass, you know that how much they will measure on if they stand on the scale, because the acceleration is 9.8 meters per second square. This is the weight they're going to get, right? This is the weight they're going to get. So it's approximately 500 newtons roughly, and you can convert newtons to pounds. That could be a simple Google, you will be able to convert that. So really the more direct conversion is 1 kilograms of mass will give you about 2.2 pounds of weight if you measure that. So if someone weighs 120 pounds, you know that their mass would be this much kilograms, okay? So that's a conversion. So just be careful, mass and weight are two different quantities, and we don't want to be confusing them. Okay, so now we know how to calculate gravity. We can do more in our analysis. Here we're doing Newton's second law application, but now we're going to break down the left-hand side into multiple forces. So for example, here you have an object, this is an object you're interested in with mass M being pulled by a tension cord. So there's tension in the cord at a speed that is increasing upward. It's being pulled up and also the speed is increasing. How does the tension compare to the gravity? All right, so let me see. Okay, so I'll give you minutes to think about this in your breakout rooms. I should be fairly straightforward. And when you come back, we can vote, okay? All right, so take a screenshot if you need before you head out to your breakout rooms. So maybe a minute and a half on this question. Hello, what do you guys think here?
Yeah. Right.
I was thinking maybe A.
Yeah.
Let's see. I think this kind of looks like one of the questions on the pre-lab, and so I'm thinking A.
A is correct. Very good.
Okay.
So how do you convince other people that A is correct? What would be the reasoning that we use?
So the cord is pulling the mass upward. I'm trying to see. Let's see. It's pulling the mass upward. So the force is going to be the mass times the acceleration.
Mm-hmm.
And then I forgot what that means for the tension exactly.
Yeah, so there are many forces on an object. In this case, are the tension, there's the gravity. Two of them are acting in opposite direction, with sort of competing effects. But we know overall, now if they're equal, you're not going to get any acceleration, right? If gravity wins, then you're going to have an acceleration downward. But tension wins, so you're going to have an acceleration upward, right?
Okay.
So
yeah.
acceleration will be pointing in the direction whichever force is bigger. So yes, in this case, we do have an upward acceleration, right?
Yeah.
Yeah, very good. Okay, I'll see you guys in the main session. I'll see you in a bit. All right, so people have already all come back. Please put in your vote. All right, so let's run the clock for 10 more seconds. All right, any last minute vote? All right, I'll go ahead and end this. So you can see the results seem to be quite, it's not controversial. A lot of you all agreed on choice A, where the tension is bigger than force of gravity. So can anybody tell us, we know that there are two forces acting on the object. So if I were to draw this, I will say I have force of gravity pointing down, tension is pulling it up. Now, knowing that these two are opposite directions, so right, it's going to be sort of competing effect. If they're equal, then it's not going to give you any acceleration. If gravity is bigger, then the acceleration should be downward, right? Tension is bigger than the acceleration, then the net force, F net. So how do you write the F net? And so I'm gonna use this as opportunity to show how we're going to put that into your equation. Is let me say this is my positive direction. So if this is a positive direction, the tension is positive, then gravity is pointing down. So that direction is reflected by adding a minus sign in front of my gravity. So I need minus mg. So then these are two forces coming together. That is giving me my net force, F net. So F net becomes T minus mg, okay? And that equals ma, so acceleration would be, in this case, also upward. And how do we know the acceleration is upward? Which part of the, does the question tell us, or are we just assuming it's upward?
Since it tells us that it's increasing in speed, and so since we're not changing direction, we know that the acceleration will be positive.
Okay, so you have a speed that is increasing, which means my acceleration is in the same direction as the velocity, and velocity is up, being pulled up. And it's not only being pulled up, but it's also being speeding up. All right, so the acceleration must be in that direction as well. Very good. So let's say, so the correct answer is A. I'm going to modify this question, okay? I'm going to modify to an object of a mass m is being pulled up on the cord at a speed that is decreasing. So I changed that one word to decreasing. Now, which one of these answers is correct? Is it A or B or C or D? You can just type your thinking or shout it out or whichever you think. So if I had changed the problem to one word, increasing become decreasing, what would be our choice? How to compare to force of gravity?
Tension would be less than the force of gravity.
Oh, tension will be less. Very good. In that case, you can see any in the context of comparison, it's easy for us to know. The problem, if it were given to you by itself, it may be more confusing because if you think about pulling up, you might still was thinking about acceleration pointing up, but no, that's the direction of the velocity. Is the velocity is decreasing, your acceleration in that case must be down, right? So in that case, your tension would be smaller. Very good. So if that is the case, the answer would be B. So tension would be smaller than mg. So you can see that I can change the problem and you should still be able to do it. What if I change the problem again? I say an object of mass is being held by a cord and is being lowered down at a speed that is increasing. And in that case, what is your answer? A or B or C? So let's do this a step at a time. An object is being lowered down. What is the direction of the velocity?
Negative, the negative y direction.
Going down, very good. So in that case, it's being lowered down. I know this is my velocity. And at a speed that is increasing, sort of it's going down further, speeding up. So what is the direction of your acceleration?
Also negative.
Also down, very good. So in that case, acceleration is down, then the gravity would be bigger. So in that case, I would still choose B, where F of G is bigger than tension. Now, last modification I make to the problem, there are only so many ways I can change it, is an object is being lowered down by a cord at a speed that is decreasing. Now you know that, then velocity is still down, then acceleration is up because it's decreasing that velocity, so acceleration must be up. Now you would choose A because the tension must be bigger. Okay, so no matter which variation of a question you are given, if you follow the sort of the logical path we took, we will always be able to get the answer. Don't try to memorize it because it's very easy to get it wrong if you're trying to memorize it. The answer is A for this one. Right? This one is going up and increasing. That's relatively less confusing. So, okay, now let's do a step further is we can actually solve for this tension. Right? I give you a little bit more of the information that we know the mass is 0.5 kilograms. We know it's being pulled up of a speed that is increasing at this rate. The rate is every 5 meters per second of increasing every 10 seconds. So we want to solve for the tension. I'll give you a minute to think about this, try to set it up, and then we will work on it together. So usually when we do this in class, I will give this as a handout. So at home, if you want to print out the handout, it's uploaded on the Canvas site, so you can go ahead and download and print it out if you wanted to have an opportunity to try to solve it on your own. Okay. All right, think about how you would draw the free body diagram, and we will go from there. All right, so let's draw the free body diagram together. Okay, so when we have a force problem, the first thing we do is draw a picture and label the forces. So while labeling the forces is our drawing a free body diagram. So you can draw it separately, or you can put your forces on the object. Either way is fine. I'm going to say there are two forces on the object. One is tension. One is the force of gravity. And that's the first step. Draw your free body diagram, label your forces, and choose your positive direction. I'm going to choose upward. You can always choose in a different direction, downward. Okay, but here I'm just going to do upward. So, and then the second step is, okay, think about the physics. What kind of physics is involved? Well, first of all, certainly Newton's second law is involved. Let's try to do that first. Because here we're trying to relate force to an acceleration, F net equals ma, right? So let's apply Newton's second law on this object. The left-hand side is net is sum of all the forces. You have one that's tension, you have another one that is gravity. Because this is upward is positive, tension is positive, gravity would be a negative mg. So that's your left-hand side. That is all your forces, F net. M is given, acceleration is something we need to solve next. So we know that in order to solve for the tension, right? We just need to do MA plus MG. We know the mass, we know what G is, we just need to know the acceleration. Okay, so does it tell us anything about the acceleration? It does tell us the rate of change in speed. So we know that the physics involved in that is the kinematics. In particular, we will look at the definition for acceleration is the change of velocity over time, right? So if you want to know the magnitude of the acceleration, just take the magnitude of the change of velocity over time. And what is the change of velocity? It's 5 meters per second every 10 seconds, right? So it will be 5 meters per second divided by the time 10 seconds. That is 0.5 meters per second square. That's your acceleration. So you can put that back into this equation and plug in your numbers, 0.5 kilo and half a meter per second plus 9.8, that is little g, and you can calculate that to be 5.25 newtons. So that is the magnitude of your tension. So you can see that is our direct, it's an application of Newton's second law combined with some kinematics to solve a problem. Okay, so now let's look at another one. This one, we will not be able to completely solve it at this point, which is fine. But again, I wanted to model the steps of how we go about doing a Newton's law problem. You have a book that the weight is given to you. Okay, so that is the gravity. 2.5 pounds is the gravitational force of the book. If you need the mass, you can find that. But that is a weight. You slide across the table, so you are holding this book at all times. Slide it across at a constant velocity. So that is important information because whenever I see constant velocity, I know acceleration is what? Is 0. Okay, and tell us something about the the coefficient of kinetic friction. We're not there yet. We haven't talked about how to calculate kinetic friction, but the coefficient simply tell us how rough, how smooth or how rough the surface is. How rough or how smooth you have for the surface. Right? If there's ice, then it's very smooth. If there's wood on the wood table, maybe a little bit more, it's a little bit more rough. But if you have like a carpet and something else like sandpaper, that would be much more rough, right? So it really just describes what kind of surface you have. The question asks, what is the magnitude of the normal force acting on the book, and what is the force that you applied? Okay, so first step is always draw a picture, help you visualize the situation and label all the forces. And here, the forces on the object, we have, of course, gravity. Of course, we have normal force because touching the ground, and you have the force by your hand. You also have friction. So these 4 forces you identify is the forces acting on the book. Okay, so now we will go. The next step is apply Newton's second law to solve these 2 questions. Okay, we will pick that up next time on Friday, or you can try to do it, solve it on your own. And we will continue to do more and more Newton's laws problems because here that is a rich topic, and you will see a variety of different scenarios. All right, so that's all for today. I'll see you guys on Friday. Have a good rest of the day, everyone.
Thank you, Professor.
Bye-bye. You're welcome.
Professor, could you go back to the problem that we were doing about the tension that we were solving for it?
Yeah.
Okay. Sorry, the Zoom chats are in the way. How did you get 5.25 for tension? I got 5.15.
Oh, That could be just a get 5.15. I might have just punched it wrong or something. And 10 point, let me see. Oh, I see. Yes, I got 5.25 because I round G using 10.
Oh,
Um,
okay.
Okay, 5.15 then.
Okay. Sorry, I just didn't know if I had done something wrong.
No problem.
Okay, thank you. And then the slides, you were gonna post them today, right?
Yes.
Okay, cool. Thank you, Professor.
Yeah.
Have a good day.
Professor,
Yes.
I'm still a little bit confused about the difference between the weight and the mass, because I noticed that for the mass you weighed it in kilograms and the weight was in pounds. So I just kind of wanted to, because either way you can, yeah, because like I'm not really understanding the difference, because either way, like you can convert it one to the other. So I was confused on that.
Right, but the thing is, you can convert, but they're not the same. That's the problem. That's the question. Is, for example, if I tell you the mass is 0.5 kilograms, then you cannot write. For example, weight is equal to 0.5. So that would be wrong, right? You need to convert it. What is the weight? Weight is mass times little g. So that is your weight, right? If you have a mass, you can convert it to weight. Likewise, if you're giving a weight is equal to 2.2 pounds, okay, then you cannot write mass is equal to 2.2 kilograms or 2.2 pounds, because pounds is a weight, is not a mass. So that would be wrong. But instead, you will write mass is actually 1 kilograms of mass. So 1 kilograms, if you buy 1 kilograms of apple and you put it on your scale, it will read 2.2 pounds. Well, actually, the scale that measure the weight. We sometimes at grocery stores, they have the mass pound. That's very confusing, okay? If you weigh it on the bathroom scale, it will read 2.2 pounds. That means you have bought a 1 kilograms of apple. Does that make sense?
Okay. So then if we were given a scenario in which like it would ask us to find the mass and we're given a weight, then we would just have to convert it to the proper units.
Yes, that's correct.
Okay, thank you.
Yeah.